Today we're going to talk about Kepler's laws. So back when Kepler was around in the early 1600s, there were two different views of how orbits worked. The Ptolemaic system was really put forth by the church, in which the Earth is the center of our solar system, and all of the bodies moved around the Earth in interesting orbits. But when Kepler came along, he basically changed that view. So when Kepler got a bunch of data on different planets and moons around Jupiter, he put together that all of these different things are following the same idea of how orbits work. But he saw Mars, and Mars was a little bit hard to explain because if all the orbits were given as like circles, then Mars didn't fit in right. And so he had to change his thinking about how orbits actually work, and that led him to come up with his three laws. So Kepler's first law is that orbits are never circular. They are elliptical. And that was one of the first things that he noticed about Mars, is that it doesn't follow a perfect circle. It's much more elliptical than, say, Earth's orbit around the sun. And when you start talking about ellipses, then you need to define some different things. So you have a minor axis, which is the little axis, and then you have a major axis, which is the longer axis. Then you have these things called focuses or foci, which basically help you define the ellipse. And then objects orbit around one of the focal points in the elliptical orbit. That is a defining characteristic of an ellipse and of the orbit. The major axis is actually split in half, and that's called the semi-major axis. And this is one of the most important measurements in an orbit, is the semi-major axis. Almost everything is defined off of the semi-major axis. And so it is half the major axis length. And we'll talk about how to derive that in just a minute. The defining characteristic of what an ellipse is, the reason why it is an ellipse, is because you take these two focal points, and if you draw a line from one focal point to the body and the other focal point to the body, and you measure those two line lengths, R1 and R2, as it's moving around that orbit, R1 plus R2 stays exactly the same all the way around the ellipse. And so as it gets closer to R1, the length to R2 grows, and so still R1 plus R2 stays exactly the same. The ratio between the semi-major axis, the long axis, and the semi-minor axis, the short axis, if those were equal to each other, it would have an eccentricity of 0. It would be a perfect circle. So eccentricity is a way to define how flat the orbit is, and the larger it is, the more oblate it is, so the more squished it is. And so you could see for Earth, it's pretty close to 0. It's 0.017. For Mars, it's much bigger. It's about like 6 times bigger than it is for Earth. So it's a little bit more oblate or a little more squished. For Pluto, it's 0.24, which means that it's very squished. Pluto has a very elliptical orbit. When we define which body is which, so we have the main body, which in this example is the sun, and that is the thing that is being orbited. And so the Earth in this case is the orbiting body. When the Earth is closest to the sun, that is called the perigee. And when the Earth is furthest from the sun, it's called the apogee. And that actually, those two locations, perigee and apogee, happen on the major axis. And if you take the perigee distance and the apogee distance, you could see that when you add them together, you get the major axis. And then if you divide that in half, or take the average of the perigee and the apogee, you get the semi-major axis. So you can define this semi-major axis, which is a defining characteristic of the orbit, as the perigee plus the apogee divided by 2. Kepler's second law is defining how fast things move as they move around the object. When it is closest, when it is at perigee, it moves the fastest. And when it is at apogee, it moves the slowest. And his law specifically says that when you're closest to the planet, you're moving very fast and you sweep out a lot. And then when you're far away from the planet, you're moving very slow and you get this thin sliver. But if you take the area of those two triangles, you get the same area in the same time. And there's a complicated formula which describes that. But basically the concept is when you're closest to the object, you're moving fastest. When you're furthest from the object, you're moving slowest. His third law basically says if the orbits were circular, then the radius, the semi-major axis, as that radius goes up, as the semi-major axis increases, the orbital period also goes up. And he gives a formula for it, which we'll talk about. So basically what this means is that the definition of a year on Mercury is different than the definition of a year on Earth. Mercury moves around the sun very fast, while Jupiter moves around the sun very slow, and that has to do with the semi-major axis of the orbit. If we zoom out even further and we look at all of the planets, we can see how the planets are laid out in our solar system. They're spread way out, and so near the sun, with Mercury, Venus, and Earth, you have years which are very short, and then as you get out towards Pluto, you have years that are very, very, very long. And so these are all measured. So Mercury's year is only 88 days. Mars's year is about 2 of our years, but Pluto goes around the sun once every 248 years. It takes a very, very long time for Pluto to go around the sun because Pluto's semi-major axis is very, very, very large. So his third law can be defined with math, which tells you basically how long the orbital period is. And so we can use the velocity and the distance to calculate a time, so an orbital period. So the velocity we've talked about is the square root of gm over r, and the distance is 2 pi times r, so that's how far it goes along a circle. And so the time is distance divided by velocity, which is shown by this equation. And then when you square that, you take out the square root, and then you can solve these things, and you get that t squared is equal to this sort of complicated formula, 4 times pi squared times r cubed divided by gm. And so Kepler's third law specifically says that the square of the period is proportional to the semi-major axis cubed. So it's a little complicated, but it basically says as you go further and further and further away from the body, the period becomes longer and longer and longer. In summary, Kepler's laws help us to quantify orbits. Those 3 laws help us to define how orbits work, and they help us to predict the locations of satellites throughout time. Further, they help us define the periods of an orbit and basically how those satellites will move along their orbits. They provide a framework for understanding how orbits work.